So let's study the same material, the design of latch and flip-flop from the book slides, and we will repeat the same concepts with some slight difference in notations. So this is the outline: sequencing elements, max delay and min delay, and clock skew is something that we have not discussed before. So you will see what is clock skew. So basically, sequential logic has two kind of let's say presentations. One is a pipeline presentation or design, in which you have this sort of arrangement that you have a register, then a combinational logic, then a register R2, then a combinational logic 2, then a register R3. They all are in the same sort of direction. So this is a pipeline design. And then the second design is sort of this feedback, or this is called FSM. So these both are sequential logic. So this is our combinational logic and this is our register. So we will see what are the design methods that can be used for both pipelined and finite state machines. We will focus mainly on finite state machines in the next lectures. So one thing that is sort of related is about let's say sequential elements. In sequential element you process the states. So you have like this state which is processed by combinational logic. So this goes to a combinational cloud, then another state, then another combinational cloud, and so on. So these stages or states are processed by combinational logic. Similar kind of effect can be obtained from what is called wave pipelining, and this is some detail that you can study, that the fiber optics works on the wave pipelining principle. So you fire the pulses of light to transmit information, and the transmitter and receiver are perfectly synchronized. So this is another kind of sequential design. This is again some text that introduces mainly the sequential logic overhead, and we will see what we mean by sequential logic overhead. So you can read through the text. Let's spend some time here. This is basically the difference between a latch and a flip-flop. So on this side we have a latch, on this side we have a flip-flop. And what happens to the timing diagram is this one. So we have, if we consider this is our input D, the output of latch is here. It is in the red box. So you see that whenever the clock is 1, the latch is transparent. So you see the clock is 1 here, okay, and the latch passes this information. So whatever is on the D, it appears here. Whatever is on the D, it appears here. At this point in time, the clock goes to 0, and whatever is in the latch, it remains stored. So we have discussed the operation of latch before, but if you consider the flip-flop, it is working like this, that on each positive edge of clock, it goes and samples the input and places that value at the output. Okay, it goes, samples the input and places that here. Okay, so one operates on the positive edges, the other operates on the levels. So one is level sensitive, the other is edge sensitive. So we discussed the design of a latch using a mux in the previous lecture, which was this design that you have on the zero a feedback path, and then you have this clock or gate signal, and this is our Q, this is our Q prime. So that is a D latch. Let's discuss some other ways quickly in which we can design the D latch. One way that was used in 1970 was a single NMOS. So the gate is connected to your clock or clock signal, and the input and the output are connected to source and drain. The advantage is that it is tiny and low clock. It does not load the clock. This is our clock signal. And what are the disadvantages? You know that NMOS cannot strongly pass a 1, so there is a threshold drop. There is the fact that it is non-restoring. There is also the noise from the output that can affect the input. So backdriving, output noise sensitivity, it is dynamic, and there are diffusion capacitances. So these are disadvantages. The next design uses the transmission gate. Again, there is no voltage drop because zero is passed by NMOS and 1 is passed by PMOS, but it requires inverted and non-inverted clocks. Okay, then you can add a buffer, or sorry, a NOT gate here, and this NOT gate has this advantage that it becomes restoring. So basically this is our transmission gate, and in front of the transmission gate you put a CMOS NOT gate, so it becomes a restoring circuit overall. You can also put it at the input and you can fix some of the problems. But if you use a NOT gate, the final output is inverted. Now this is another design that is the first one that uses feedback. Okay, so all the designs in this lecture which does not have feedback, okay, they are not reliable. If you want to store a bit reliably, by reliable I mean for a long duration of time, you should use feedback. And actual and practical latches that are used today, they cannot be designed without feedback. So this is a design in which we have a transmission gate, and then we have back-to-back inverters. So this is a design that is more stable, and it uses again these clocks. You can also add another inverter here. The inclusion of this inverter results in the output to be non-inverting. So now the output is non-inverting. Okay. If you want to increase the drive capability, so if you want to attach multiple things, multiple fan outs, then you can add another inverter here, and this design is widely used in actual manufacturing. So this is one way you can manufacture the latch, no back driving. Also, this is another, in this design we have this inverter. Another design is we don't have the inverter here at the input, so the output is inverting. The advantage of this one is it is smaller, it is faster. Okay, the downside is that the input is unbuffered, so you have inverting outputs. We also discussed the flip-flop. Remember that we designed the flip-flop from this circuit. So we had this D latch, here we have 1, and we said that if we combine 2 of these, we can, so this is our clock signal, here we put an inverter, here no inverter, and this is our let's say this is our master, this is our slave. So we designed the flip-flop from a mux using this method. The same goes here. We have this one master, we have the slave, okay, and note the clock inversion. So here at the bar we have a connection to NMOS, and here at the bar we have a connection to PMOS. So it acts as an inverter. This is again another flavor. We have the master, we have the slave. Again, the basic thing is feedback. So you either feedback that one, the first one. This is not a good design because it is not reliable. It cannot store reliably for longer duration of time. But this is reliable because it has this feedback. Okay, so this is the flip-flop design. We can also because you see there are flip-flops, the one that we discussed only have D, Q and clock signal, but there are some other signals that are in the flip-flop. For example, we can have enable signal, we can have reset signal, we can have set signals. So there are different flavors of the latch and flip-flop. This is one which we have this enable signal. This is another, this is the symbol, and this is how we implement it. So if you want to add the functionality of enable, you can add a feedback mux to the latch. Now inside this latch can be any of the circuit that we discussed previously. It can be based on NOT gates, or it can be based on muxes. This is another way that we can enable, just through an AND gate. Similarly, for flip-flop, we can use a feedback mux, or we can use an AND gate. So there are some of the methods we can add the enable functionalities. Similarly, we can add reset functionalities through an AND gate. Okay, so this is synchronous. This is for a latch. This one is for a latch, and this one is for flip-flop. And you see it is written synchronous reset. So a synchronous reset is a reset which is only considered when a positive edge of clock arrives. So for example, consider that this is considered, let's say this is our reset signal. Okay, and here is our clock. Okay, so positive edge for, and let's say this is our output. So if it is a synchronous, let's say QS means synchronous, then the output would stay, stay, let's say 1. Okay, let's say this is the some previous value, and when this point comes, this positive edge comes, the output will become 0. So it is reset here. It is not, although reset is 1 in this duration of time, but it has already missed this positive edge. So on the first edge it was 0, so it is not considered, and on the next one it is considered. Now if it was an asynchronous reset, the behavior would have been something like this, that it is 1, and whenever the reset becomes 1, the output simultaneously becomes 0. So the first design is for synchronous, the last design is for asynchronous reset capability. Okay, you see the difference is here. If you want asynchronous, you have to add the reset capability in the feedback path. Okay, while in the about designs, the reset functionality is not included in the feedback path. Similarly, you can add set and set functionality. So you see it is through this or this design, so you can analyze the design. This is how you can add different inputs to a flip-flop. You can study this. Okay. Now there are different ways in which you can design your sequential logic. In fact, there are 3 ways in the book. One is that your model is like this, that you have register R1 and you have register R2, and inside these 2 registers you have your combinational logic. This is one way, and this is predominantly the most used way. So all your logic is inside flip-flops. The second way is to use 2-phase latches, in which you have this latch L1, latch L2, latch L3, and L1 is driven by a clock of phase 1, L2 is driven by a clock of phase 2, L3 is driven by a clock of phase 1. Okay, so your cycle time is the same, so it is from here to here. So how it works is when the phase 1 clock has a 1, the phase 2 clock at that point is 0. So it means that the phase 2 is in memory mode. So what happens is that in phase 1, when phase 1 is high, the combinational logic 1 computes. Okay, then there is some non-overlap time, so to enable the combinational logic to process the information and be sure that it is processed. Then when the phase 2 is 1, the combinational logic 2 starts processing, and when the phase 1 high again arrives, so the latch becomes transparent again and information goes outside. So this is 2-phase clocking, and you use latches that are driven by different clocks. Then there is a pulsed latch, in which all the latches have the same clock, but they are used as a short pulses. So the clock is high for a very short duration of time. Okay, so every one of these have different advantages and different disadvantages, but the most frequent one that is used in digital design is flip-flop based. So we will mainly focus on the flip-flop based. This was also discussed in the previous slides. So I told you that the book uses slightly different notations. Some of these notations are for latch, so latch only. So for example, these 2 are for latch, so they are applicable to 2-phase design and pulse design. So I will leave out these 2, and the rest are TPD is the logic propagation delay, TCD is the logic contamination delay. In the previous slide we called this TPD L and TCD L. L for logic. And latch/flip-flop clock to queue propagation delay. So it is TPCQ. In the previous slides we call this TPDR, where R stands for register. So TPDR is also called TPDR, or TPD rich is also called TPCQ, where P stands for propagation and C stands for clock to queue. Okay, so the time from clock to queue output. Similarly, TCD rich, here it is called TCCQ, contamination delay from clock to queue. Okay, and I am leaving out these two because we are not going to study in detail the pulsed and two-phase designs. And then we already discussed the setup time and hold time, and there is no change in the symbols for these. Okay, so we already have discussed these graphs, which were slightly different because they used this notation, TPD and TCD type notation for rich and conventional logic. Again, what is max delay? Max delay is TPD. So TPD is also called max delay. And if we are interested in what is the so consider this model. This is our RTL model, in which we have two flip-flops, F1 and F2, or Ridge 1 and Ridge 2. So call it Ridge 1 and Ridge 2, for example. And inside we have the combinational logic. So how long or how long can be our clock? So our clock is basically, you see, the time that it takes for TPCQ, which is same as previously we called this. Let me write it in another color. So previously we called this TPD-R1. So this is the same as TPD-R1, and plus, so in that amount of time your data goes from here to here. Okay, this is called TPCQ. Okay, then from here to here it goes in amount of time that is called TPD. Okay, previously we called this TPD logic. Okay, and then when it reaches here, it should be stable. Q1 should be stable. Sorry, D2, this node is D2. So D2 should be stable before the next clock by an amount of time that is called T setup. Okay, so this was the formula that we discussed before, but it uses this time slightly different notation. So if we want what is the maximum TPD from this equation, so it is basically T setup plus TPCQ. So this quantity is called sequencing overhead. Okay, so this is the max delay. Okay, let's calculate the min delay. So by min delay we mean TCD. Okay, so again we already talked about this. The second formula was if you remember that if we have this kind of connection between R1 and R2, then TCD of R1 plus TCD of logic should be greater than T hold of R2. So if I replace it with the quantities that are used by book, so it will be TCCQ plus TCD should be greater than T hold. Okay, so if I'm interested in TCD, it should be greater than T hold. The main delay is T hold minus TCQ. I can take TCD on the other side, TCQ on the other side, and it will become TCD is greater than equal to T hold minus TCCQ. So it is the min delay. Now when you have a complex chip in which you have a single clock that is coming, and you have this chip in which you have a lot of flip-flops, so it is going here and it is also going through a lot of ways here. Okay, so ideally, theoretically, this register R1 and register R2 should get the clock at exactly the same time, but due to the physical distance, which is this wire is a very long wire, because you know that information travel inside a chip at the speed of light, but all this information is happening in nanoseconds. So even a slightest delay between here and here, between R1 and R2, if they do not receive the clock simultaneously by let's say tens of picoseconds, then this can result in the information being processed wrongly. Okay, so this is called clock skew, and this was not evident before, but as the transistors kept smaller and smaller, and the chip became denser and denser, this became an issue. So if we have a clock skew, for example, consider these multiple highs. So let's say this one, the clock can go high here or here or here or here. Similarly, it can fall here, here, here. So there is an inherent differences between the rise and fall times. So this amount of time from here to here, this is called T skew. Okay, so now this difference should be included in the clock period. So now if I am interested in the clock period should be greater than equal to TPCQ, which is the propagation delay of register, plus TPD, which is the propagation delay of logic, plus T setup, which is the setup time of my register, plus T skew. So now my clock period should be greater than this extra quantity, and now I can find the sequencing overhead or the max delay to be increased by T skew. Similarly, for the whole time, a factor of T skew will be added to this one also. So this is the summary of this part of lecture. We have not discussed this and this in detail, because the most widely used one are flip-flops, and on the formulas for these we have discussed in great detail. We haven't discussed the concept of time borrowing, because a time borrowing concept is only applicable to two-phase and pulse latches, and it is not applicable to flip-flop. It is 0 for flip-flop. That's why we have left out time borrowing concept. but we have these formulas. The only one that I have discussed are related to flip-flops, so you can expect some problems related to the application of these formulas. One example I have already solved in the previous lectures. So this is all that I have to talk about. So we discussed the design of D-latch, and we discussed several designs based on feedback, based on non-feedback, based on mux, based on inverters. We designed flip-flop from inverters and from mux. We added several signals like set, reset, and all those things. And most importantly, we discussed the timings. So all the details about setup time, hold time, and how to find the maximum frequency, and how to ensure that the chip is working. So in order to ensure that the chip is working, the hold time constraint is very important. Okay, with this I finish this part of the